This video will look at Hertzsprung Russell diagrams, named after Ernst Hertzsprung and Henry Norris Russell. There's a couple of things before we talk about the diagrams we have to know about, and that is the temperature of the stars. Quite often, when we talk about really hot objects, we call them red. Now, it's not the case all the time. The hottest stars are actually blue. And so, if we look on the right hand side of the screen here, red objects here will be a lot cooler compared to the blue objects. And so, as we increase temperature, the colour changes, with the most temperature being blue, and then white, and then yellow, and then orange, and then red. And we see this really in reflection. We look at in your chemistry lessons. We light a Bunsen burner, we open up the air hole, lots of oxygen in, the flame is blue, and we heat up substances, liquids on the blue flame. When we close it, we have the yellow, orangey safety flame, which we do not heat objects with because it's cooler. And so blue stars, galaxies, are a lot hotter in temperature than red. And so we have a scale here. In actual fact, the blue objects here are classified as O, and they're at over 33,000 Kelvin. White objects are classified called B, and they're between the 33,000 and 10,000 Kelvin. Then we have white objects classified as A, between 10,000 and 7,500. And then we've got F, which are yellowy white, and they're between 7,500 and 6,000 Kelvin. And then we have objects that are around about the yellowy orangey colour, and they're from 6,000 Kelvin to 5,500. And we have objects that we classify as K, and they're orangey in colour, and they're from 5,200 Kelvin to around about 3,700. And objects that are stars that are red classify as M, and they're from around about 2,000 Kelvin to 3,700. But as I say, the blue stars that appear blue, they are at the highest temperature. And then we look at the idea of what we call absolute magnitude. Now, stars that appear closer to us will often appear brighter. So it doesn't really help with classification, especially with the temperature of stars. And so we look at an idea of called absolute magnitude. And this is really, and this is a definition that we have to be aware about, it's a measurement. It's a measure of the brightness of the stars at a standard distance. So if all the stars were at the same distance away from Earth, that's what they would appear like in terms of their colour. So really, in other words, they're at a fixed distance. Now, quite often we'll see that the brighter the star, if we look in the night sky, that depends on its size and or its surface temperature. And we can relate to this to this column here and this column here to depend on how bright the actual star is. And quite often we'll say that the bigger And the hotter it is, the brighter it will be. And that kind of makes sense to us. But also at the same time of that, the brighter it is, the closer it's going to be as well. But when we look at this, this is the contradictory bit to this, is that when we refer back to the absolute magnitude, even though it's closer, it's going to have a lower absolute magnitude. So even though it's bigger and hotter and brighter and closer, it's going to have a lower absolute magnitude. And that's when we come across what we call like the Hertzsprung Russell diagrams. And you'll see a diagram like this, either of what's in orange here or in blue. And we can look at the luminosity here, and that's really how bright they are, or looking at the absolute magnitude. So the luminosity we can see here is in that logarithmic scale, and it's in orange, and we've got the absolute magnitude here that's in the blue. But whatever it is, it's the same pattern that you've got to be able to learn, and that is that in this first area here, we're going to have those white dwarfs. And white dwarfs are in the bottom left-hand corner. And we will know that when we reflect on these, that they are very hot, all right, but they're small, and so they're quite dim. And then we have in the middle, that really goes from top left to bottom right, we have these idea of these main sequence stars. And the main sequence stars are here, and our sun is around about in this position here at the minute. So that's our sun. And these main sequence stars, like I say, they go from the top left to the bottom right. They're roughly the same size, and so the brighter the star, the higher the temperature will be. And above those, we have the red giants and the red supergiants. And what's key about these is that they are a little bit cooler, but they're large in stature, and they are very bright. We know they're very bright because of their luminosity is over here compared to the white dwarfs that are down here. And we can see the temperature, the key bit here, the temperature is unusual, is that the higher the temperature is on the left hand side, and it's cooler over here. So you're just going to have to be familiar with that and know where to put the white dwarfs, the main sequence stars, and the red giant and red supergiants. Right. I hope that helps explain the Hertzsprung Russell diagrams. So you've got to know the temperature of the stars, that blue has got a higher temperature compared to the red orange stars, the definition of absolute magnitude, and whereabouts stars might appear on the Hertzsprung Russell diagrams. Good luck.